One photo, no special camera rig, full 3D depth. That's what a new imaging technique is promising, and once you understand how it works, it's kind of hard not to be impressed. So let's start with the basic problem. When light hits a camera sensor, everything gets flattened. A ball close to the lens and a wall far behind it both end up as flat pixels. The camera doesn't know how far away anything was. It just records color and brightness. That's the jump from 3D reality to 2D image, and normally, information about depth just gets lost in that process. Now there are ways to recover depth. Stereo cameras use two lenses side by side, kind of like your two eyes, and compare the slight differences between the two views. LiDAR fires lasers and times the reflections. Structured light projectors beam patterns onto surfaces and measure how those patterns distort. All of these work, but they all need extra hardware. Extra sensors, extra processing, extra complexity. What if you could do it with just one ordinary snapshot? That's the question this research is trying to answer. And the key piece of the puzzle is something called a coded aperture. Here's what that means. The aperture is the opening in a camera lens. Normally, it's a clean circular hole. Light passes through evenly, and things that are out of focus get that soft, round blur you've seen in portraits. A coded aperture is different. Instead of a plain circle, the opening has a pattern cut into it. A deliberate, carefully designed shape with specific holes and blockers arranged just so. That pattern changes how blur looks in your photo. When something is out of focus through a coded aperture, the blur it creates has a specific signature. It carries the fingerprint of that pattern. And here's the clever part. How blurry something looks depends on how far away it is from the focal plane. Things close to the focus point are sharp. Things farther away blur more, so the blur is actually encoding distance information right there in the image. It's hidden in the pixel data, but it's there. The challenge is pulling it back out. That's been the hard part for decades. Researchers have tried to decode these blur patterns mathematically. The problem is it's messy. Real scenes have overlapping objects at different depths. Light from a blurry background bleeds into sharp foreground edges. Textures can look similar at multiple depths. Traditional algorithms struggle to untangle all of that cleanly. That's where the AI comes in. The team trained a neural network to look at images taken through a coded aperture and learn what the blur patterns at each depth actually look like. Not just in ideal controlled conditions, but across real messy scenes with varying lighting, textures, and complex geometry. The network learns to recognize the depth signature hidden in the way every patch of the image is blurred. What comes out the other end is two things at once: a sharp, clean color image with the blur removed, and a depth map, a full picture where every pixel has an estimated distance value attached to it. Bright means close, dark means far, or the other way around depending on convention. Either way, you've reconstructed a 3D understanding of the scene from a single flat photo. Now, previous attempts at this have existed. Depth from defocus is not a brand new idea. But the accuracy and reliability have historically been the weak point. Edges would come out smeared. Thin objects would disappear in the depth map. Highly reflective or transparent surfaces would confuse the algorithm entirely. This new approach is claiming to push past a lot of those failure cases, and the results in the research look noticeably cleaner than earlier methods. So why does this matter? Let's think about where you'd actually use this. Robotics is an obvious one. A robot arm that needs to pick up an object has to know where that object is in 3 dimensions. Right now, that usually means adding a depth sensor, calibrating it to line up with the color camera, and dealing with the cases where the depth sensor fails, which happens a lot with shiny or dark surfaces. A single camera that inherently captures both color and depth simplifies that whole pipeline. Autonomous vehicles are another. More depth sensing from a single camera is always useful when you're trying to build a picture of the world around a moving car. Medical imaging is where this gets really interesting for a channel like ours. Endoscopes and surgical cameras are tiny. There's no room to add a second lens or a laser emitter. If you could give a surgeon real-time depth information from a single small camera inside a body, that could genuinely change how minimally invasive procedures work. You know whether that instrument is 2 millimeters from tissue or 10 millimeters. That kind of spatial awareness matters a lot when precision is critical. Augmented reality headsets could also benefit. Getting depth right is one of the hardest parts of making virtual objects look like they actually sit in a real physical space. The coded aperture approach has one practical trade-off worth mentioning. You're changing the optics of the lens. That pattern in the aperture does affect how the camera performs in other ways. Low light situations are harder because you're blocking some of the incoming light, and the AI model needs to be trained on images from that specific aperture design. Change the pattern, retrain the model, so it's not a drop-in upgrade for existing cameras. It's a design decision you make up front. But for devices built from scratch with this in mind, the trade-off might be very much worth it. One sensor instead of 2. One stream of data instead of needing to fuse a color camera with a depth camera. Simpler hardware, potentially lower cost, and fewer points of failure. What's genuinely exciting here is the direction of travel. We're at a point where AI isn't just processing images after the fact. It's being paired with optical hardware designed from the very beginning. The lens and the algorithm are being co-designed together. The physical optics encode information in a way that the AI is specifically trained to decode. That's a different philosophy than building a camera and then throwing software at it afterward. It's computational photography taken seriously at the hardware level, and the results are starting to show it. One snapshot, hidden in the blur, the whole shape of the world, and AI smart enough to read it.